Hello, everybody. My name is Ben Cranston, and I am going to be doing part one of this homework about vectorization, the Jacobian, Frene Serie, and 3D plotting. I'm really excited to get into this, so without any further ado, let's start talking about the problem a little bit. So I need to generate the surface coordinates of a helical pipe of a cross-sectional radius with the cross-sectional radius of 0.5 with a central helical curve defined by the following parameters in T. And these are like the x-coordinates, the y-coordinates, and the z-coordinates. Part 1, which I will be doing this class, I'm going to use closure to explain and code a higher-order function that accepts a function and returns a function that calculates the Jacobian of the central helical curve, which is what I'm doing up here. Compare your results in Part 1 with that obtained via automatic differentiation with JAX. So there's really two, or I guess three parts. The first one is generating this plot, or three subparts to part one, you could say. I'm going to generate this plot. Then I am going to make this higher order function to calculate the Jacobian. In this case, the Jacobian is the same thing as the gradient, but I'll explain that more later. And then compare my results in one with that obtained via automatic differentiation with JAX. So without any further ado, let me go ahead and start to create this helical pipe. So I'm going to start out by just creating a function of the helical pipe. And it's not going to be like the full wireframe thing. I'm just going to, I've lost what I was saying because I started typing. I'm just going to generate a line first. So I need to import numpy as np. Numpy is a Python library that is just really great for doing computations, particularly array computations. It's going to run for a minute or two, or okay, got it done. And so now I can go ahead and start to put in these functions. So I'm just going to go ahead and start out by typing in these functions. So x equals radius times numpy's cosine function of t, which we haven't defined t yet, but I'll get to that. Y is going to be something very similar, but with numpy's sine function for t, and then z is going to be some slope in the z direction times t. Now this is going to get mad at me because t isn't defined. Neither is r and neither is z. So I'll go ahead before this and define t as something. Then I will define r as something and define the slope and the z direction as something. By the way, r is the radius, t is like a time, but I'll get into t more later. So let's go back here and look at this. Well, the radius is just 3. That's saying the radius of this helical curve that we're trying to generate that's going to go around. The slope in the z direction is 0.4. This is controlling like how fast the pipe is rising, essentially, because z is the height direction in this case. Usually you say y is the height, but in this case it's just simplest to have z be the height. When Python loads in the chart, it's going to put z as the up-down axis initially. You would have to do some stuff to change it, so I'm not going to mess with that. But anyway, I will go ahead and define t using something called numpy's linspace function, which, if I could spell it correctly, linspace, thank you for helping me out, appreciate it. So we need a starting condition, so we'll say it starts at 0. I don't exactly know where to end it yet. I actually do, but I'll get back to that later. And it'll go from 0 to 1, and it will have 100 increments. This is going to be like 0.01, 0.02, 0.03, all the way until it hits 1. That's what this is saying. So r is 3, as it says earlier, and the slope in the z direction is 0.4. So if I go ahead and run that, I should be able to get these x, y, and z coordinates. And now I'm ready to go ahead and plot it if I really want to. So I will come up here and I will go to a Plotly. I'll go to a Python library called Plotly. And I'll actually go to its Subplots library. From that library, I'm going to import a function called make subplots. And this should like it. Okay, yeah, it likes it. And so now I'm going to take fig, which is a generic name for a figure, and I'm going to define it as a subplot. Make subplots. This should work. Yeah, okay, so now Fig is a subplot, but it doesn't have any data. So I'm actually going to need to add some data to Fig. And so I'll do that using the add scatter condition, or I don't know exactly what it's called when you do like add something like this. I don't know what that's called, but I'm going to do it anyway. So we'll say that the x coordinates come from this x array, the y coordinates come from this y array, and the z coordinates come from this z array. So x equals x, y equals y, and z equals z. Great. So now I can go ahead and run that, and it didn't like it for some reason. That's weird. Oh, okay. So first off, I'm not just adding a scatter. I'm actually going to add a three-dimensional scatter plot. So that. Yeah, that was the issue. Okay, cool. It needs to be scatter 3D, not just scatter. And as you see, we have a bunch of points. They're kind of sloping a little bit, like they're kind of curving a little bit, but this isn't a full helical curve. And that's because I didn't really define t correctly. See, the issue is t, the way you're putting t into this cosine function and the sine function, t is acting as a radian. So we need to define t in terms of radians. And 1 radian, or I guess you don't define in terms of radians, but you need to put it in like radial numbers. And 1 radian equals 2 pi. Remember, if we go back to like high school pre-calculus or whatever. And so I need to go from 0 to 1 radian, which is actually going from 0 to 2 pi. So numpy also has a pi function. And I'm going to go ahead and take this 100 and change it out with an n. This will become important later when I'm trying to generate like the chart. But I'll keep it with 100 points. So we can go ahead and run that, run this. And now we have sort of a full sloping chart. So that's awesome. That's fun. This is kind of what we're looking for. I'll go ahead and change it to 4 pi. Just to get 2 full rotations. That's cool. You know, I like that a little bit more. And then I'll also go ahead and just for preference of what I want to look at, I will change the mode to lines. And that should, yeah, okay. So now instead of having all these dots, these big fat dots, now it is just a line. So I want to go ahead and take this helical curve, right? And my end result, this isn't what I'm doing in this video, but my end result is I want to have like these circles around it, going all the way around it. I want to have this wireframe of circles going all the way around here that show like the physical boundaries of the pipe. And this will look really cool. You can spin it around and it'll do this cool corkscrew thing. Like it's going to be really fun once I get this done. And so, yeah, I'm pretty excited to be able to do that. But how am I going to be able to get all these like points dotted around a line? Like that's going to take so much computation to be able to do. I'm going to have to do so much like, okay, at this point I need to add some values, subtract some values, and go up and down. And there's just going to be such a hassle to be able to do that. But there's actually a much simpler, well, maybe not simpler, but there's a more straightforward, less programming intensive, less labor intensive way to get this done. You just have to understand some array multiplications and some array math. And that's kind of the whole goal of this homework, is to understand the Jacobian, Frenet-Serre, 3D plotting, all these various things that are really going to help me get to the bottom of building this like helical curve. And so, first off, the way I'm going to generate these points is I want to find a plane that's tangent to the line at any given point. So I'll say, okay, I want to be able to say, at this point right here, so at x equals 3, y equals negative 1.4, z equals 5, approximately, what is the, what's the plane that's like perfectly tangent to the line at this point? And then how can I get that at any given point? I think there's an argument or something going on outside my apartment. That's kind of funny. I don't know. They're yelling about something. I don't know what. I'm trying to see if I can see the people. I don't know. Maybe you all didn't hear that. I hope you all didn't hear it. I think he said a couple curse words. That would be inappropriate. But anyway, I want to be able to do that throughout this whole line. And yeah, that's kind of my end goal for this whole project. And so the way I'm going to do that is by looking at the derivative of the line. And so what is the derivative? Well, Wikipedia is here to save the day. We got this. So this is the definition of the derivative. So this is saying the derivative at a point A. So the derivative of f at at a point A, so this is like the definite derivative. This isn't an indefinite derivative or anything like that. Is equal to the function of A plus H. H is an infinitely small value. That's what this limit is saying. Minus f of A all over H. So this is saying, what's the difference between point A and a point infinitely small after A? There might be a good visualization of that here. I'm not quite certain. Maybe there is. I don't really see anything here that is a great visualization of that point. But you can kind of see here the derivative is always tangent to the line. So if we can take the derivative in multiple directions, so if we can take the derivative in the x-axis, the y-axis, and the z-axis for this 3D curve, then we can get a line that is, we can get a line that is tangent. Well, not a tangent, but I guess the derivative isn't tangent. The derivative is going to be, what's the word for it? I forget. But anyway, we're going to be able to get this plane. And we'll have to do some matrix multiplication and all that. But anyway, kind of the issue with the derivative is you can only go relative to one direction at once. So if I were to take the derivative of this... actually, let me backtrack a little bit, and I'm going to make up a new function. So I want to say, I'm going to create a new function just to sort of explain this. And this is going to be f in terms of x and y. And that's going to be equal to sine of x plus cosine of y. And actually, let me check my notes real quick. Yeah, okay, I set that up correctly. Or I set it up the way I've been practicing it. I just wanted to make sure it's just a very minor thing I wanted to make a note of. This is all I have over to the side. It's just some quick notes about what I've been working on. Just some quick, like, whatever, like the gradient is equal to this. And just so I don't have to do a bunch of math in my head as I'm trying to solve this all out. And so we have f of x, f in terms of x and y, equals sine of x plus cosine of y. So if I were to take the derivative of this, so if I were to say df relative to x, then that's just going to be negative cosine of x, right? And if I were to take this derivative relative to y, so let's say, I'll just copy this just to make it quicker, but relative to y, then it would actually turn into, it would turn into negative sine, I believe. Let me Google that real quick. Of cosine is negative sine. Yeah, okay. So that would turn into negative sine. This would turn into cosine. But the point I'm trying to make is that when you take the derivative relative to x, this just becomes 0. And when you take the derivative relative to y, this just becomes 0, right? That's the way derivatives work. And so that can kind of cause us a number of issues, right? Because we want to get like the derivative of the whole line. And so this isn't, the derivative isn't necessarily what we're going with here to try to find a tangent line. Instead, we want to find something called the Jacobian. I'll skip to the Jacobian. The Jacobian is a matrix of multiple derivatives. And what the Jacobian is saying is that it's the change in function 1 over the change in independent variable 1, all the way through all the independent variables relative to the first function, all the way through all the functions relative to the first independent variable, all the way through all of the functions relative to all the independent variables. So in this case, x and y are my two independent variables. In this case up here, x and y and z are my independent variables. And I'm using the term independent variable kind of loosely here. That might not be the best way to describe it, but that's what I'm going to call it, just for consistency. And so let me go ahead and program out this f function in Python. So we will define f as a function, and that function returns sine of x plus cosine of y. How are we going to do that? Well, I'm going to go ahead and define x as x0. So x is actually an array of the various independent variables. And then y I'm going to define as x1. So this is the first value in the array. The second value in the array is equal to x and y, respectively. Now also, sine and cosine aren't just built in, so I need to take NP sine and NP cosine. But yeah, now that I have this, I will have this function of f. And this is just something we'll practice to find the gradient. Specifically, I haven't addressed the gradient yet. The gradient is similar to the Jacobian, but it's just for single functions. So if there's just one function, f, what is that function relative to each independent variable? So what's the change in f relative to the first independent variable all the way through all of the independent variables? So in this case, it would be df over dx and then df over dy. So there's only two independent variables. But this is what we want to find. And I want to, as this says, using closure, explain a higher order function that accepts a function and returns a function that calculates, this is a typo, I believe, the Jacobian of the central helical curve. Okay, so I need to say that the Jacobian and the gradient are the same because there's only one function in the example we're looking at. And yeah, compare my results with what is obtained via automatic differentiation, which basically JAX has a built-in function that does exactly this. But I'm going to go ahead and write my own function first. And so let's go ahead and just call this function gradient, grad for gradient. Define gradient in terms of f. So I want to pass a function into gradient, and then I want gradient, this function, to take some independent variable, or to take like a list of two definite independent variables, or however many there are, and return to me a function. So I define gradient. I need to have a function inside of this function, so I will define get the gradient. This is the part that will actually do some of the calculations. And I'll define it in terms of x, which is just the independent variable. So once again, let's go back to the derivative, because I need to go through and progressively take the derivative relative to different independent variables. So first x, then y. But I'll just create something that iterates through them. We have this L. It's the limit h approaches 0 of f of a plus h minus f of a all over h. So I can go ahead and start to program that. First off, I need to define h. What is h? Well, I could try to do something with a limit, and that would just be really annoying. Instead of defining h as something that approaches 0, I'm just going to say that h is very close to 0. So I'll say 1 times 10 to the negative 10. And that's h. So it's a very small value of h. I'll have to do some mental rounding. A lot of this will come out. Like if it's 1, it'll say it's 0.99999 or something like that. But this is h. So this is our very small difference between point A and A plus a very, very tiny difference. Remember, that's what the derivative is. And so now that I have h defined, I want to go through this. And actually, well, before I do that, I'm going to define res as a blank list. And that blank list is just going to be something that I'm going to use to store the values. So it's going to have 2 for this f. But that's neither here nor there. And then I'm going to go for, if I can spell correctly, for I in a range that is the size of x. So x dot size. For I in a range that is x dot size, I am going to iterate through. And so I'm going to say that I'm going to take, like, the derivative, right? So what's the derivative? Well, I will say that the derivative, I probably didn't spell that correctly, but that's okay, equals f of x plus h plus f of x, and then I'm going to divide that whole thing by h. I'm actually going to put some spacing in here just because I think it looks a little bit better. Then I'm going to take res and append it with the derivative I found here. So res.append with the derivative, and then that should be good once it's gone through the whole list. So then this get gradient is just going to return res, and then the whole function is going to I can't spell. Return is something I have to spell correctly because it's built in. But res is going to return get gradient. Sweet. So I can go ahead and run this, and the function should run correctly. Unfortunately, this math is not correct, which I will demonstrate in a minute. But the function ran at least. So let's go ahead and set this up. So I will say that the gradient of f is equivalent to grad, and then we're going to pass the function f in there. I can run that, and it likes it. I'll go ahead and create some initial conditions up here. So we'll call that x0 is a numpy array of 2 values. So the ones I was practicing earlier that I already kind of have memorized are for numpy pi and numpy pi. So this is saying the initial conditions, x0s, are x equals pi and y equals pi. And initial conditions isn't exactly the word. This is like x0 is the point at which we want to find the derivative. So we want to find the derivative when x equals 0 and when y equals 0. And that's like what we're trying to find the gradient of here. So I have that now. So now I can go to f grad, and I can give it these initial conditions, right? And so I'll go ahead and run this. And I get numbers that super aren't correct. That's kind of funny. This isn't even what I was expecting to get. So, yeah, what's going on here? We got this derivative. H is a very small number. Okay. It's peculiar. I was expecting to get the numbers like -1 and 0 or something like that, which still aren't correct, but okay. Huh. Well, anyway, let me explain what's going on here for a second. So we have this function f, right? I already explained that pretty thoroughly. I'm taking the gradient of any function, which I just happen to use the same term, f, for it. It's going to define h, define this blank res, and then it's going to go through each time and sort of calculate this x plus h, f of x, and then divide the whole thing by h. Oh, okay, here's part of my problem. So, oh wait, no, that's not an issue. That's all correct. Dang. I thought I found it. Yeah, I'm not quite sure what's going wrong here, but, anyway, what I actually need to be doing here is I need to go in and create a copy of x and define that as x plus h. So if I go ahead and say x plus h is equal to a numpy's copy function of x. So I'm going ahead and defining x plus h. Then I can take this x plus h and plug it into here. When I run that, I should get maybe something a little bit different. No, it's basically the same still. Okay, well this is getting a little bit weird. Let me keep going. So we have this x plus h, which is a copy of x. And what I'm basically trying to do here is, I didn't actually define x plus h. So if I go ahead and say that x plus, oh my goodness, I can't type today, plus h at whatever I is, so for whatever I is in the range, is equal to x at whatever I is, plus h, which is once again that very small value. I will go ahead and maybe try to calculate this. And once again, I'm getting weird numbers that don't quite make sense still. It's just kind of annoying. I will have to, after I do that, I'll have to go ahead and set x plus h back equivalent to xi, just to set it back to being correct. So I do that, and I probably am still not going to get the right numbers. Yeah, okay, so this is kind of weird. This isn't what I'm not certain. I must have been doing something wrong then. Something different than what I was doing when I was practicing this, that's for sure. F seems the same. Gradient seems the same. Equals a copy. What does x look like in this situation? Can I get a view of this, please? Okay. Okay. Well, let me pause for a second, and I will circle back around and figure out what I'm doing wrong here. So this is one of the most weirdest, unexpected errors I've ever seen. I had done this exactly correct, exactly the same way I've typed it in the past, and there wasn't really a difference. But up here, it's reading this wrong. Like it's reading this not as it's reading h not as 1 times 10 to the negative 10th. It's reading it as 1e, which is somehow a number on its own, minus 10. And so I think if I were to run this again... Okay, now it's working. Anyway, I believe it was reading h wrong, because I had this exactly the same as I've been doing it in the past. But somehow things weren't working out correctly. So 1 times 10 to the negative 10th power is what I was really trying to get at here. It's a very, very small, close to 0 number. And so then when I run this function and I look at the initial conditions, we will get a solution. And that solution is saying that the derivative of this f function, when x is equal to pi and y is equal to pi, the derivative is negative 1 in the y direction and 0 in the x direction. So is that correct? Well, I have done the math over to the side, over here. I don't know how well you guys can see this. Let me get a look. Maybe you can, maybe you can't. I don't know. I did all this cosine, sine stuff, just calculated it out with the calculator, essentially. And if I go ahead, I'll read it off real quick. You'll see that the gradient of that f function, when x and y are both equal to pi, the derivative in the x is going to be cosine of x. The derivative of y is negative sine of pi, something we've already established. And that is going to be equal to negative 1 and 0, which, sure enough, is what my function returned to me. So that's great, that's fun, it's all fine and dandy, but the problem I guess I'm really having here is, well, I guess there's no problem. What I now want to look at is Jax's gradient function. So Jax.grad. What is Jax? In short, Jax is similar to NumPy. It's a library of functions that allow you to do some really cool multiplication and matrices type stuff. But Jax is really designed for machine learning, and so it's very efficient. It runs much faster than NumPy does. And it's not really important for this application or any other application, but my professor, Carlos, really wants us to use Jax. So I'm going to use Jax's grad function, which is short for gradient. So first off, I need to import Jax. So I will just go up to the top, go back up to the first column where I was doing import, and import Jax. Sweet. And then I also need to import, if I go down one, I actually need to import Jax's NumPy function. So import jax.nuc, I'm not spelling anything correctly today, as JNP. This is just Jax's sort of variation of NumPy, and it's called, I'll call it JNP, which is a pretty common abbreviation. And so, yeah, we spent all this time programming out a function, and now I'm just going to do someone else's, use someone else's function. So feeling pretty good about that. First off, I'm actually going to rename this function custom grad. So this is the gradient function that I wrote. I'm going to go ahead and run that just to get rid of grad, because Jax actually uses the grad, and I don't want to overlap, really. I think that could cause some issues. Go ahead and redefine it there, and everything works out still. And so now I can go ahead and, first off, well, actually, I'll go ahead and try to program it out beforehand. So let's look at this documentation real quick. We need to pass a function. We need to pass some conditions, and everything else isn't really important. So I will just say that Jax gradient is equal to Jax dot grad, so the Jax gradient of f. If I go ahead and run that, it shouldn't give me any errors. Yeah, it doesn't, but there actually is some huge errors in here. And so I'll say Jax grad of some x values. Sorry, my nose is kind of itchy. And so I'm going to just give it this x0, and now it should give me an error. Yep, sure enough it does, but this is the error I expected to have. And so basically there's a lot of stuff here. Basically what all this is saying is that my function up here, f, is not compatible with Jax, because Jax actually needs to have its own set of functions. Jax has its own version of NumPy. That's why I imported Jax NumPy. And so I actually need to go ahead and set everything up. Instead of being a numpy cosine, numpy sine, whatever, I'm going to set it up as JNP, Jax's numpy. And that's just going to let Jax do all these matrix multiplications and all the things Jax wants to do. It's going to let Jax compile it the way it wants to and do all this other stuff. So I copied F from up here down here, and I'm just going to rename this F Jax to indicate this is F in Jax's terms, and I'm just going to change it to JNP cosine and JNP sine. And so this is the same F. In fact, I will even go ahead and copy this over here. It's the same F, but now it is in Jax's terms. So pretty sweet, right? Well, we need to give it F Jax instead of F. So Jax gradient is equal to Jax.grad of F Jax. And now this should maybe work? Yeah. Okay. Sweet. Sweet. So, going back here, we said that at the points pi, so x equals pi, y equals pi, this function, the gradient of this function, is going to equal an array that looks like this. So, -1 and 0. Now, sure enough, when Jax has its own way with this problem and finds the gradient of that same function, it's going to have -1, basically the same thing, obviously some rounding differences, but basically the same thing, and then very, very close to 0. I mean, times 10 to the -8. So there's also something about, this is a float 32, I think that has to do with how it's calculating, or something, I don't really know, to be honest. So yeah, this is using Jax's gradient function, or even like programming my own gradient function, to find the point tangent or the derivative to a function at any given point. In the next part of this video, I will be using Jax's Jacobian function in order to find the tangent, normal, and I'll be putting that all in like a Frene-Serre function. But that's all I have for right now. I really appreciate you watching and giving me some time, and hopefully you learned something. I certainly did, and I hope that you have a wonderful day. Bye-bye.